Hello everyone, my name is Zaywen. I'm from the University of Western Australia. This is a joint work with my student Han Feng and also my collaborator Professor Wei Cai. First, I would like to talk about some background and then our proposed techniques, experimental results, and finally with a conclusion. Swarm intelligence mimics the behavior of social animals to achieve the intelligence for the whole group, basically. Within the group, the individuals will need to exchange information in order to achieve the group intelligence. Particle swarm optimizations is a type of swarm intelligence algorithms and is simple but effective, and it has wide range of applications. Basically, to can be using any search algorithms. For example, the search for neural architectures and the update of the swarm, so which is one step on in the PSO algorithms, can be extremely slow. So especially when we are dealing with high dimensional problems or we are having a large number of particles. So here particles can be the beads, the ants, and etc. And we have done some search and on like the popularity of these PSO algorithms, and the number is based on Google Scholar. So the x-axis is number of publications, and y-axis is the year. So from 2010 to 2020, as we can see, the number of publications has been quite large. It's almost always more than 10,000. So this number is based on Google Scholar. As you can see, the PSO is still an active research area, or at least it has been widely used in the community. This is an example about the swarm intelligence in the context of using ants. So there are the current global best position for the whole swarm and also a local best position for each particle, and a list of visited positions. So for each ant, they always have their own local best position. And in this example, ant two, so the local best position also the global best position for the whole swarm. And so as we can see, so for example, in ant three, the direction to the global best is different from the direction to its local best. So each end will combine these two pieces of information and then to form the to obtain the best position for this end in order to reach the global optimal. The particle swarm algorithm optimization involves four steps. The first one is initialization for all the particles and then evaluation for the whole swarm. And the third step is to update the local best position and or the global best position. And finally is the update for the whole swarm. And we have done some bottleneck analysis for this algorithm. So there are four steps. The third step is to update P-best and G-best, which is relatively cheap. The most expensive part is the swarm update and also swarm evaluation. The initialization also contribute to some cost. And so this is the four problems that we use in our experiments. Okay, the PSO algorithms, basically the goal is to find the global optimal by the particles, and each particle has a velocity which is a vector and also a position and also a vector. So this is the formulas to update these two informations which maintained by each particle. We will look at the details of these formulas later on, and we have more explanations in our paper. So in terms of GPU accelerations, we can dedicate one GPU thread for each particle. And also because the swarm update is the most expensive components, so we can use GPU for that step, and also the CPUs are for the rest. And similarly, one GPU thread for each particle during the swarm update. So in our implementation or in our algorithm, we use one GPU thread for each dimension of a particle, which is the finest granularity for this PSO algorithm in terms of. And this is the overview of our method. So basically, all the four steps can be done on GPUs. The initialization essentially is just some number generations, and then the swarm evaluation is can be performed on the GPUs, and basically doing a function calculation. We also design a nice schemas which can allow developers to easily use change to another function, and also the finding the local best, the global best is just a parallel reduction. And finally, the swarm update, we use the element-wise operations. We model the problems in this way so that it can be well parallelized on GPUs. And similarly, it also involves some number generations. So this is the key overview of our method. For swarm initialization, basically we are initializing the positions for all the particles and also the velocity of the particles. It also involves two other matrices, which are the local best and global best, need to be used in the formulas. That's all for the initialization. In terms of swarm evaluation on GPUs, we use one GPU thread to evaluate the fitness of one particle. We also design a schema which allows practitioners to customize the evaluation functions. And the swarm update can be modeled as an element-wise operations, and we have seen these formulas previously. Every particle has a velocity and position. So these are two vectors. So if we put all the vectors together, they become matrices. So these are and in the paper we discuss how to model these problems as an element-wise operations, and then we can parallelize that on the GPUs. And also in terms of the workload allocation, so if the problem becomes very large, we cannot fit all the, we cannot create one thread for each element in a particle. So we can using these formulas to limit the total number of threads that we need to use in our implementation, so that it will not run out of memories. So the velocity and also the positions will need to be constrained within a range. So this is equations that need to use when we are updating or initializing the velocities of each particle. And in the paper, we also try to use shared memories and tensor cores to optimize this PSO algorithms. So basically, using shared memory, if it's too large, the size matrix is too large, we need to break down into some matrix. And similarly for the tensor cores. And in the paper, we also discuss how to use memory caching to reduce GPU memory allocation. Experimental results, we conduct experiments on these GPUs and also compare with all three. And these are some typical problems for swarm intelligence, or some search problems or optimization problems. And so basically we want to find the optimal values for these three problems. And the thread conf is case studies that we try to use this PSO in real world applications. We have more discussions in our paper. So we have four baselines. Two are on CPUs and the other two are on GPUs, and we implement our algorithm using CPUs in sequential version of on CPU, and also OpenMP version running on CPUs, and the last one is on the GPU. So this is the overall comparisons that we can, as we can see, our algorithm on GPU is almost always the farthest one. And in terms of speed up, as we can see, again, the farthest GPU baseline, and we are 5 to 9 times, 5 to 7 times speed up. And compared to the CPU-based versions, we can achieve 100 times speed up. And we also compare the errors that we search, and as we can see, so we produce similar results to the baselines, and also more reliable results, as we can see from this table. And finally, we also have studies on like why our algorithms is faster. So it's mainly because of the throughput to the memories, and in terms of total number of G flops, different algorithms they have very similar um, G flops. So that's because we don't change the algorithm itself, but try to use GPU resources more efficiently. So the main part is we increase the bandwidth. Okay, in conclusion, we present FastPSO. We locate the bottlenecks of this algorithm and also investigated different techniques to accelerate it on GPUs, and we conducted experiments to study the efficiency of our techniques. So that's all. Thank you very much.